Okay, ma. Last class we have seen IEEE 754 standard of representing a real number, right? Um, we have two formats as we mentioned. 32-bit width format we call that as single precision IEEE standard, and 64-bit format we call that as double precision IEEE standard. Okay, single precision, double precision. So in single precision, 1 bit is for sign, 8 bits for biased exponent, 23 bits for your significant field. So that here any number is represented as plus or minus based on the sign component. Okay. So plus or minus 1 whole power, the sign bit, most significant sign bit, 1 dot, your significant field, number of bits which are of, these bits are of 23 bits into 2 power. Here we are representing binary, so the base is 2, so 2 power. You'll be having the biased exponent is available in the sign component. So our true exponent I need to place here. So what is the true exponent? It is nothing but biased exponent
minus bias.
minus bias value. Okay. So with this we'll be getting your any number. Any real number can be represented like this in 32-bit width. Okay, so here bias value is 2 power k minus 1 minus 1, where k gives you the number of bits reserved for exponent. So for single precision format, k is 8, so the bias value is 127. Okay, so for bias value 127, the possible true exponent values are, see, as we are reserving 8 bits for biased exponent, which can take a values range from 0 to 255. So possible exponents are, by subtracting 127 from which I'll be getting minus 127 to 128 plus 128. These are the possible values. Okay. So with this implementation, we can have numbers which are in a range like this. So we have represented on the number line maximum and minimum, both positive side and negative side, and we concluded that there is a possibility of not covering a certain range of regions. Those are 5 regions totally: 0, negative underflow, positive underflow, positive overflow, and negative overflow. Right? Okay. So, but 0 is very important for us for representing 0, and whatever is the number that representing beyond this and beyond this. Okay. So, as infinity, plus infinity and minus infinity and 0, to facilitate for assuming representing these numbers, out of all the possible combinations of your biased exponent 0 to 255, okay, out of which 0, which is nothing but all 0 component, and 255, which is nothing but all ones. Okay, so these two are reserved for representing 0 as well as infinity. Okay, so for representing 0 and infinity, the exponent, all zeros and all ones are reserved. Okay, so that we have a possible biased exponents out of 256 combinations. 2 are reserved for representing 0 and infinity, right? So in what way means, okay, in binary 32-bit format, in single precision, right? So a 0, which is positive 0 if your sign component is 0, and your biased exponent, all 8 bits, if they are zeros, and the fractional portion, if it is also 0, then we are assuming the value to be 0. Okay. So actually, as per the notation, scientific notation, we'll be having plus or sign bit, 1 dot your fractional bit into 2 power true exponent, which is nothing but biased exponent minus bias value, of course. Okay. So if this is 0, and if it is 0, and if it is 0, because 1 dot, you will be getting a value of 1. Okay. And 1 into 2 power minus bias value if biased exponent is 0. Right? So that value is resulting, it is not 0, but we are assuming it to be 0. That is one adjustment done in IEEE 754 standard. If all are 0, the value is considered as 0. If sign component is 1, the value is considered as minus 0. Similarly, if the biased exponent all ones, sign and fraction values are 0, the value is treated as infinity. Similarly, minus infinity for the sign bit 1, and all the biased exponent bits are 1, and fractional bits also 0, then we are representing minus infinity. Okay, right? So 0 and infinity, both positive and negative, are facilitated with the help of all 0 biased exponent and all 1 biased exponents. Okay. So there are a few other erroneous to represent the erroneous values. Okay. So we have NaN. It means not a number. Okay. NaN, not a number. Q, quite a NaN, signaling NaN. Two possibilities are existed. Sign can be 0 or 1. Exponent is all ones, and fraction is not 0. Okay. Fraction is not 0. If the first bit is 1, it is quite NaN. If the first bit is 0, it is signal NaN. Okay. So two separate kinds of not a numbers are provided. Depending on the application, depending on the value that we are resulting, QNAN or SNAN are available. Okay. So these are application dependent notations. Basically, NaN is not a number. Right? This is 32-bit single precision format. See, whenever we resolved 0 and all ones for representing 0 and infinity, right? So out of 256 possible combinations of your biased exponent, 0 and all ones, all zeros and all ones are reserved for 0 and infinity. So the available biased exponents are 254 only, right? Right? Okay. So which have a range of biased exponents start from 1 to. Allowable biased exponents are 1 to 254, right? 1 to 254, from which you have to subtract your bias value, which is 127. Then 1 minus 127 results to minus 126 to, this is plus 127. Okay. So the true exponents now have a range minus 126 to plus 127. Earlier it is minus 127 to plus 128. But in IEEE, one adjustment has done all zeros and all ones for reserving infinity, 0 and infinity respectively. Okay. So possible or allowable exponents for true actual exponents are minus 126 to plus 124. Is that clear?
Yes, ma'am.
So these are now different parameters under single precision. Okay. A storage bit is 32-bit. Binary 32 means single precision floating point format. Exponent bits are 8. Exponent bias, that is 2 power k minus 1, which is 127. Maximum exponent is now plus 127. Okay. So because these two all relates to actual. Okay. So we have biased exponent range from 1 to 254. So subtract 127 from which we'll be getting minus 126, which is the minimum exponent, and maximum exponent is plus 127. Okay. And approximate normal number range base 10. So with which we can approximate what is the number. See, we got our number 1, comma 2 minus 2 power minus n, right? Into your exponent you have to mention, right? So the exponent size it varies from 2 power 2 power plus 127 in positive sign, 2 power minus 126, very least value. Okay, so with which after converting them to decimal, these are the values: 10 power minus 38, comma 10 power plus 38, normal number range. Okay, from here to here, this is the total range in base 10. Okay, trailing significant width, which is of 23 bits, number of exponents 254, number of fractions 2 power 23, right? Because we have 23 bits reserved, so total number of different fractions 2 power 23. Number of values, these many values in this range, how many values we have? Smallest positive number 2 in 2 power minus 126. Largest positive number, this is the value. Okay, largest positive number 2 minus 2 power minus 23 into 2 power 127 you have to apply, then I'll be getting this value, right? So this is the maximum value for which if you apply maximum exponent, which is nothing but 2 power 127. So into 2 power 127 if you apply 2 power 128 minus, here n is 23, right? You have to subtract that, I'll be getting 104. Okay, so this is the largest positive number. Similarly, you can have even the negative side, you just apply minus to it. You will be getting largest negative number minus of this value and smallest negative number minus of this value. Okay, so this is in single precision, which is 32-bit width. Similarly, if we go for double precision, which is of 64-bit width. In double precision, out of available 64 bits, 1 bit for sign component, 11 bits for biased exponent, 52 bits for your significant field. Okay, so 11 bits are dedicated for biased exponent, so that the bias value is 2 power 11 minus 1 minus 1. Okay, so 2 power 10, which is nothing but 1024 minus 1, which is 1023. Okay, so bias value is this. Coming to biased exponent, so 11 zeros to 11 ones, so 2 power 11 different combinations we may have. 2 power 11 means 2046 different combinations, right? Out of which here also all zeros for representing plus or minus 0, all ones of the exponent for representing plus or minus infinity. So if we take out, then we may have biased exponents which can range from 1 to 2044. Am I right? 2044. Right? Am I correct?
Yes, ma'am.
2044. So you have to 2 power 11. How much? 1024 into 2. Right? So 2048. 2048. All ones 2047. This we are reserving. So this is 2046. Right? Am I clear? So 2 power 11 is 1024 into 2. 2048. Okay. So these many number of exponents may have, which range from 0 to 2047. This is 11 zeros. This is 11 ones. Right? 11 zeros for representing plus or minus 0, 11 ones for representing plus or minus infinity. Okay, so leaving these two values, our biased exponent can have values range from 1 to 2046, right? So our true exponent now, biased exponent minus bias value. Our bias value is 1023. You have to subtract it. So it is minus 10222 plus 1023. Right? So these are the true exponents, possible exponents, actual exponent values. Am I clear?
Yes, ma'am.
So with this, now get the values, compare the tables. So here the storage bit is 64 bit double version format. 11 bits for your exponent bias is 1023, right? Since it is 2 power k minus 1, here k is equal to 11. And next, maximum exponent 1023, minimum exponent 1022, right? So because exponent 11 bits are reserved, so I will be having 2 power 11 possible values range from 0 to 2047. Okay, so this and this value for extreme values. So 1 to 2046, you have to subtract the bias value, which is 1023. I'll be getting minus 1022 as the minimum exponent and maximum exponent plus 2023. And this is the approximate total number range, right, under base 10. And coming to the significant width, which is 52 bits, and number of exponents are 2046, right? So possible exponents are from 1 to 2046. 2046 exponents are available. And coming to the fraction value, different fractions, 2 power 52 different combinations we may have. Number of fractions are this value. And coming to the number values, this is the value. You need to apply the same formula. 2 minus 2 power minus n is the maximum value. This is 1. This is for the case of significant. You just apply the power of your exponent for minimum and maximum base, including the sign plus or minus. Then I'll be getting the extreme values in both the ends. Apply them on the number line. You'll be getting the smallest positive value and largest positive value. These are the values, right? So this is double precision format. So the same context, how the extremes are used here also in the same way the extremes are used. Plus 0, minus 0, plus infinity, minus infinity, and quite none and signaling none. Okay. Let us see the examples. So one example that we have already seen. Let us do that also. IEEE standard of binary floating point format represent minus 20.5 with both single and double precision. Okay, you have to represent both 32-bit and 64-bit width. Similarly, 45.3 and the reverse process. Okay, so if they have given 32 bits, which represents IEEE 754 32-bit floating point format, calculate the decimal equivalent. Okay. So these two, I feel that you can do because we have already done in the last class. So let us do this example in the reverse process. Okay. So you have to first extract the components out of the 32. This is the most significant bit that represents the sign. And next the bias value, since 32, so the bias value, biased exponent is of 8 bits. Okay. So this is your biased exponent. And remaining everything is your significant field. Okay. So now what is your decimal number? Your decimal number is equal to minus 1 whole power s into significant 1 dot your significant field into 2 power true exponent, which is nothing but biased exponent minus bias value. Okay. So just replace all the values. Minus 1 whole power s is equal to 0 here. So minus 1 whole power 0 into 1 dot significant field 1 0 1 0 0 0 1. Later on all are zeros, so you don't need to mention them. And then 2 power biased exponent is this much. How much is this? You can apply powers here. Okay. So 2 power 0, 2 power 1, 2 power 2, 3, 4, 5, 6, and 7. 2 power 7, which is nothing but you see here itself you apply power or else subtract the bias value and then apply power. Both are same.
134, ma'am.
This is 134. So if
Yes,
it's
ma'am.
134, you have to subtract bias value, which is 127. Okay. So I'll be getting the result as 7
7.
0 0. Okay. So 2 power 7, positive 7, right? Plus 7. So which is equal to, now here apply powers of 2, right? This is 2 power 0 1 dot this 2 power minus 1 minus 2 minus 3 4 5 6 7 2 power minus 7. So this is 0.5, half means 0.5 plus 1 by 8 0.125 plus 1 by 2 power 7 1 by 2 power 7. You calculate that using calculator. Can you tell me what is that value? 1 by
0.0078
0.00
0078 125.
78125. So after adding
Ma'am,
all
only 2 zeros, ma'am.
only 2 zeros,
Yes, ma'am.
78125 into
Yes, ma'am.
2 power 7. So how much is this? This is plus symbol. This is plus. So how much is the total fractional part? We getting 1 dot anybody are doing?
0.6328.
This is anyway 1 plus is there. So 1 dot 6 3 2
6328.
1 2 5 into 2 power 7, which is nothing but
So,
128.
yes, ma'am.
So how much is the total value?
Two not 9.
409. Okay. So decimal value exactly 409 you got? Of course. Okay.
209, ma'am.
209.
209, ma'am.
209. Anyway, I didn't calculate it. That's why I'm asking. 209. So the decimal equivalent value of this is a 209. Like this, you need to calculate. Okay, both reverse and forward cases. Right? So with this, we have completed a floating point representation also. Okay. So if you have any doubts with this, we have completed unit 1. If you have any doubts in the whole unit 1 topic, you can ask me. Any revision on any single topic, if you have any doubt, you can ask me. Again, you will be having class on Thursday, right? So on Thursday, we'll be having slip test during the first hour, because Thursday I won't be available. Only in the learning portal, you have to attempt your slip test on unit 1. Am I clear? The slip test
Yes, ma'am.
of 20 multiple choice questions, 20 minutes. Okay, learning portal, you need to log in and attempt the slip test. See, if you have any doubts in first unit, you can ask me so that we can revise.
Ma'am, will you upload the videos from after multiplication, ma'am? After multiplication algorithm in LMS.
After multiplication,
After multiplication algorithm, can you upload the videos on LMS, ma'am?
yeah, I didn't do. I will do that today.
Yes, ma'am.
Any repetition of the topic? Any topic you want me to repeat? I will repeat now. We have half an hour more time.
Ma'am, can we do division algorithm, ma'am?
Division algorithm.
Yes, ma'am. Restoring division.
Or non-restore.
I want to do an example in each one of them.
Example for each. Right?
Yes, ma'am.
So, division, let us do first restoring algorithm. So, dividend. Tell me the dividend, any number.
200.
Louder, ma. I'm not moving.
200, ma'am.
200.
Yes.
Okay.
Ma'am.
Divisor.
13.
1, 3. Okay. So first you have to calculate them in binary. $200 in binary is 1100 1000. Right? 200 in binary is this, and the 13 is anyway 1101. Okay. So this is 8-bit width. This is 4-bit width. Okay. So we can have double the size of dividend. Okay. So everything is fine here. Right. So A, your capital A. See, we are assuming our dividend positive and divisor also let it take a positive. So AS is equal to 0, positive number. Okay. So sign bit 0. And here divisor also 0. So sign bit 0. This is the total number. And this is the total number. Out of which sign component we are separating. Right? And magnitude is this. Similarly, for divisor, magnitude is this. Okay. If you separate, after separating sign component, dividend we will load it into a Q register, right? A register holds upper bits, which is nothing but 1100, and the Q register holds lower significant 4 bits. Okay. And then divisor is available in B, which is where your BS of course is 0, and B, capital B magnitude is equal to 1101. Okay, this is B. right? So during, since it is division, we have to subtract b from dividend. So I require minus b everywhere. So I'm calculating minus b also. Okay, minus b is nothing but we are taking like 2's complement of this b. 1101, first one's complement 0010. After adding 1 to 8, I'll be getting minus b as 0011. This is minus b. Okay, and this is plus b, 4-bit value, 4-bit value. And what about the sequence counter SC? Number of bits in your magnitude portion. Here it is 4, so it is 4. Okay, these are the components. So remember the restoring algorithms. What is the algorithm first? First we will perform a division by subtracting b from a. Okay, right? We'll subtract b from a. If a less than b, you should not perform subtraction, right? Okay, but we have done the subtraction, so we will restore the dividend back by adding b, and then we'll shift left, right? If a greater than b, here itself the upper 4 bits of your dividend are greater than the divisor, we cannot perform the division. So we will make DVF, division overflow flag, as 1, and we will come out of the division. Okay, so where it signifies that the quotient is greater than 4 bits, obviously we will be getting 5 bits as the division. Okay, so hence we cannot perform the division, and we can conclude that by setting DVF flag as 1, and we can come out. Of course, at this, for this examples, we won't get DVF as 1. Okay, so now we'll start with the table inserting. I require for task, and then for E, which specifies whether A greater than B or A less than B. After that, A, Q, and then sequence counter. For that, these many fields I require. This is E, this is A register, Q register, and then SC. Okay, so first what you have to do, we have to perform A minus B. Okay, this is the first task, A minus B. Initialize the values first. After that, we start with these. E is initially 0, A is 1100, Q 100, SC 4. Okay, and first task A minus B. Okay, right? So minus B need to be added to A. Okay, minus B is 0011. You have to add. I'll be getting 1111. And what about E? E is
0.
okay. So E is 0. If there is no E, it means A is less than B, right? Okay, this specifies that A is less than B. It means you cannot perform the subtraction, but you have done. So what you have to do? You need to restore the dividend back by adding B to A minus B. Okay, so restore A. So how can you do that? By adding B, by nothing but add B, restore A. So to this we have to add B, which is nothing but B is 1101. Okay, so after adding these two, what is the result? 10 10 10 10. Okay, right? So this is 10, this is 10, and this is 11 11. We'll be getting E as 1 and 1 1 0 0. This is whatever is the previous A that we got here. Okay, we have restored A, and after this what you have to do? We have restored A. It means upper 4 bits of your dividend are less than B. Okay, since E is 0, it means your A is less than B. So it means your DVF is 0. Division overflow is 0. We can perform the division by restoring A. Means we are adding A. We got our initial conditions back. Okay. So now what you have to do now, from here actual loop starts, right? So we will shift left. We will shift left. What we shift left? E, A, Q will shift left. E will be lost. Okay, most significant bit is available here. 1, 1, 0, 0, 1, and Q is now 0, 0, 0, 0. Now Qn, which is the new least significant bit that represents the quotient part. Okay, first quotient bit is, we are assuming it as 0, right? And after that, after shift left, what you have to do? You have to perform again A minus B. In restoring algorithm, only the operation that we perform is minus B, subtraction. Okay, after shifting left, we perform subtraction. So we will add minus B. Minus B is 0, 0, 1, 1. Okay, so I'll be getting, this is 1, 1, 1, 0, 1, 0. Here I'll be getting 1, and here I'll be getting 1. Right? And what about E? E is 0. Am I correct?
Yes, ma'am.
So E is 0. So what is the decision? E is 0 means A less than B. Okay. So if A less than B, what about Qn value? Qn is 0. Right? You have to set your Qn 0. You should not modify. Qn is A less than B, so B cannot subtract from your dividend. So Qn, you have to keep it as it is 0. Okay, you should not set that value, right? Since A less than B, what you have to do?
Restore B. Restore A.
Restore A by add B, by adding B. Okay, you have to add B back. What is B? 1, 1, 0, 1. After adding this, I'll be getting, this is 1. And this is 1, 0, 0,
1, 0, 0, 1.
at our 1 back, our A back, partial remainder, which is 9 back. At this stage, it is 9, right? Before subtracting B, so that we got back. Okay. And what about Q? Q is same 0, 0, 0. Okay. We have restored and we made Qn 0 as fixed. So I'm reducing my sequence counter by 1. Okay. After that, for the next cycle again, SHL EAQ. Right? So this will be 1, 0, 0, 1, 0, 0, 0, 0, 0. Okay. Now, what you have to do? A minus B. So add minus B, 0, 0, 1, 1. After adding this, I'll be getting 0, 1, 0, 1. Right? 3 plus 2, 5. E is again 0 here. Right? So E is 0 means A less than B. So you have to restore A back by adding B. Right? So what is B? 1, 1, 1, 0, 1 is B. Add this. If we add this, so I'll be getting here 1 and this 0, 0,
1, 0.
0, which is 2 back. Okay, so why I took that much time? This is 0 as it is. So second bit is also over. SC decreased by 1. Next cycle, SHL EAQ. 0, 0, 1, 0, 0, 0, 0, 0, 0. Okay. After that, A minus B. What is minus B? 0, 0, 1, 1. If we add 0, 1, 1, 1. Here also again, E is 0. So A less than B. Restore A by adding B. B is 1101. So if we add back, we'll be getting this as 1, and then our previous A, whichever it is 0, 1, 0, 0, will has to be resulted. 1, 0, 1, 0, 1, 1, 1, 0. Right. Okay. See why the quotient is 0 every time. Am I doing correct way? Okay, let us see. 0, 0, 0, 0 only, and then reduce the sequence counter 1. Okay, next. Something is wrong. Shift left EAQ. So 0, 1, 0, 0, 0, 0, 0, 0. A minus B. Minus B is 0, 0, 1, 1. Minus B. Are they correct? B 1, 1, 0, 1. Quotient cannot be 0, no? Again, here also E back to 0. E0, A less than B, we have to restore A. So we'll be getting 1, 0, 0 back. 8. 8 and then 0. So 0, you have to stop. The quotient 0, it cannot be 0. How much is the quotient? 13 by 200 by 13. 200 by 13, how much?
15 point.
So 15 should be the quotient. All ones we should get. But on zeros.
Minus 15.
15 into 13, 195.
It's minus 15.
Minus 5. Okay, so 5 as reminder, all ones we should get. We have to do A minus B. So till here, okay. After that, we have to shift.
Ma'am,
Yes.
it is minus 15 now. So it will be stored as 2's complement.
Yes.
Quotient will be minus 15.
Quotient 0 వస్తుంది కదమ్మా, ఆల్ వన్స్ రావాలి. ఈ పార్ట్ అయిపోయిన తర్వాత we have to shift left. If E 0, you have to perform subtraction. A less than B, Qn is 0. So this is only we have done. Sequence counter reducing, not 0 repeated. We are going this path only. We won't get this path. Did we perform subtraction wrong way? We have performed subtraction. Subtraction is minus B. B is 13, 1101 minus B 0010 plus 10011. Correct. And what about A? 200 is this? Is it the 200?
Yes, ma'am, that's correct.
Correct only 200. decimal 200, binary 38, 38, C8. Okay, 1100, 100, 1100, 100. So we have to add minus b. Minus b is this only. 0011 we have added. We got this. E is 0. Okay, we have restored. After that we have shifted left. This E is 1. Okay. So here you got after shift left E is 1, right? After shift left E is 1. So after shift left E is 1, you have to subtract. After that, okay. After shift left we got E as 1, right? We have neglected this one. We go wrong path. E is 1. So after subtraction, A greater than B, because E is already earlier it is 1. So A greater than B, you need to make Qn as 1. See, after shift left, this one, whatever we got here. Okay. Right? So A minus B, we are doing subtraction A minus B. Since here E is 1, that will carry, right? So we have to make your Qn 1 and then you need to go back. This path we need to choose. So we have followed this path. We forgot initially. E is 1. So this path we have to go. After shift left, your E is 1. You are adding these values. So this is 1 0 1 0 1 and 1. E as it is. E is not updated here. E as it is. So E is 1. So you need to make your Qn 1. So you have to make your Qn 1 and then you need to decrease the counter and then go back. No need of restoring. Okay, because your E is 1, so you have to go by this path, but we have gone wrong path, restore. Am I clear?
Yes, ma'am.
So here all this is wrong. Here E is 1. This is your result. Okay. So you have to make your Qn as the next time you have to, you'll be getting 0 0 and 0 0 0 1 and then sequence counter you have to reduce. Next time SHL EAQ. So we'll be getting E1. What here? A minus B. Okay. So 1 1 0 0 0 0 0 1 0. Then A minus B. Here also we got E1 that we need to remember. Minus B 0 0 1 1. So E is as it is 1 and then here 1 0 1 1 0 0 1 0. One zero one one and now your Qn should be 1 1 because your E is 1. E is 1 kabatti Qn should be 1 and reduce the sequence counter by 2. Again SHL E equal to 1. So make Qn 1. This step is added here. SHL EAQ. So again here E1. 0 1 1 0 0 1 1 0. So A minus B. B is 0 0 1 1 minus B. We are adding. So we'll be getting 0, sorry, 1 0 0 1. Right? 6 plus 3 9. After this, since E is equal to 1, you have to make Qn as 1. So 1 0 0 1 0 1 1 1. Reduce the sequence counter. Then shift left. Again E1 0 0 1 0 1 1 1 0. After that, A minus B 0 0 1 1. So 0 1 0 1 2 plus 3 5, and here it is 1 1 1 0. Since E is 1, you have to make a Q and 1. So 0 1 0 1 1 1 1 1. Sequence counter 0. So quotient 5, remainder 15. Okay. Okay. So you need to remember this part also, that what the mistake that we have done. Is that clear, Amma?
Yes, ma'am. Thank you, ma'am.
So let us see the same example with restoring method. This is restoring, non-restoring method. See, in non-restoring, see, same values, except the E, remaining everything will be there. We won't have E here. What are the values? A is 1110, 1100. Q is 100. SC is 4. Okay. So initially in non-restoring method, first time you have to perform A minus B. Okay, after shift left. Okay. So first time, see the algorithm. Better not to do. See, first time we will perform shift left in whatever it is the case. Okay, right? So you have to perform shift left operation, and then you need to either add or subtract. Okay. So but first time you have to subtract. That was the algorithm. See, for the first time the dividend is shifted and B must be subtracted. ఎందుకంటే ఇనీషియల్ గా యువర్ Q అండ్ కోఎఫిషియంట్ బిట్స్ ఏమి లేవు. B ని సబ్ట్రాక్ట్ చేసిన తర్వాతే ఈ సబ్ట్రాక్షన్ జరుగుతుందా లేదా, that we will conclude later on, right? So first time the dividend is shifted left and then B must be subtracted. Okay, right? So this is what you have to do initially. SHL shift left 100. Sorry, 1001 000, and this is the Qnth bit that we have to decide initially whether it is 1 or 0. Okay. After shift left, what you have to do? You have to perform subtraction. Initially, subtraction is 0 0 1 1. Do this. So I'll be getting 1 1 0 0. right? Okay, so here you have to take decision. But whatever is the shifted out bit, here a less than 0. See, a less than 0, you have to shift and then you initially you have to subtract. After that, a less than 0 s. But we have a most significant bit 1. That was the mistake that we have done even in non-restoring method. This example is quite complicated. See here a minus b we are doing. We got 1100 as a result. Here the most significant bit of a, here it is 1 means it is indirectly saying your a is less than b 0, right? Result a less than 0. Based on that we will take decision. So a less than 0 means you should not perform the subtraction with which the qn we will assume it as 0. So ఇది మనం 0 చేస్తాం. But as per our result we should get 1. See why we are having this, because after shift left the most significant bit which was 1 here, that we are not taking into account. We have shifted out. That thing is not there in the algorithm. Initially itself a is less than 0. So you have to, but initially you have to subtract. That was the condition in the algorithm. ఇక్కడ ఏ లెస్ దాన్ 0 వస్తుంది. సో qn 0 చేస్తున్నాం, బట్ మనం qn 1 కావాలి. ఈ ప్రొసీజర్ not clear here. I will confirm this case later. Let me work out here.
Yes, ma'am.
Explain this because మన most significant bit shift out చేస్తే అది e లో store అవ్వాలి కదా. Based on that you have to perform the subtraction. But as per the algorithm, this is the way that we have to follow. But what about the shifted out bit, most significant bit? అది ఇక్కడ కన్సిడర్ చేయట్లేదు. ఇక్కడ అది కన్సిడర్ చేస్తేనే మనకు ఆల్ వన్స్ వచ్చినాయి. ఇక్కడ అది ఎలా తీసుకోవాలో I have to check it because in the algorithm nothing is there accordingly. Okay, so I will work out this example and I'll let you know. I'll post it in the learning portal example ఇది. Okay,
Yes, ma'am.
మీకు టైం కూడా అవుతుంది. ఎనీవే ఇప్పుడు చూసినా ఇది రాదు, ఒకసారి చూడాలి నేను. ఓకే అమ్మా, లెట్ మీ టేక్ ద అటెండెన్స్. absentees are 69, 74, 75, 86, 92, 97, 101, 102, 104, 109, 110, 112, 113, 116, 117, 119, 120, 308. Okay, ma. Thank you.
82 present, ma'am.
82 లేదమ్మా 92 absent.
Oh, okay.
82. Okay, ma. Thank you. Bye for today.
Thank you, ma'am.
But be prepared for the slip test. Thursday, first hour.
Yes, ma'am.
There won't be a class, only exam.
Yes, ma'am.